We're now recording. Welcome to week 5 of 281. Went pretty quickly. We are getting near the midterm. This week, we're going to talk about sorting algorithms, bunch of them. We got the elementary sorts and the more advanced ones. Don't be overwhelmed. I remember when I took this class, it felt like it was a lot of sorts that I had to learn. And before we go into it, remember, you don't need to memorize these sorts, but rather understand the general idea. Like on the exam, we're not going to tell you to implement Quicksort. However, we might give you a helper function and quiz you on like the underlying idea. So as long as you have a general idea of how it works, and you understand the complexities and the theory behind it, you'll be set. Okay, some announcements. Project 2 is due on the 14th. Still plenty of time, but you should always start. Students often struggle on part 2 with the end of part 2 when you're dealing with nodes in the heap. So give yourself plenty of time for that. There's some papers you have to read. If you're struggling conceptually, please go to Profis Hours. That's a great resource. Also, IAs can help too. But try to take advantage of group office hours and group Profis hours. A lot of your questions on project 2 can be answered without needing individual help, and it'll be a lot quicker for you, and we'll be able to help more students that way. Midterm on the 21st. That gives you about a week between the project and the midterm. It's a lot of time. It's a little less time if you use both your late days, so try not to use those. And it's from 7 to 9 p.m., 9:20 p.m. If you need accommodations, make sure you get those. And fall break's coming up, so enjoy your break. Maybe give yourself a little time not to study so you can relax. And yeah, any questions on announcements?
Is the exam online or?
Is the exam online or in person? It was originally going to be online. Does anyone in chat know? I am off the top of my head, I don't know. We were planning it online, but we might have switched it.
Okay, so it's still uncertain.
I've heard online, like that's what Dr. P keeps saying, like every time he says it.
Yeah, that's what I thought. I believe the exam will be online. I will double check with you at the end, but you can also check Piazza, and there should be a post clarifying all of the material about the exam.
Okay,
and the
thanks.
details. Yeah, sorry. Any other questions?
Yeah, actually, never mind.
Okay.
I'll just check Piazza. Thanks.
Sorry that I can't be more helpful. Okay. Agenda for today. We're going to first talk about the midterm, then go into some concepts with container types, then all of the sorting algorithms. We're going to talk big picture on those. Then we're going to go into binary search and the handwritten problem. So first, talking about the handwritten problem from last week, connecting ropes. So the problem itself is that you had these ropes of a certain length and you had to connect them all together with the minimum cost. The cost of connecting 2 ropes was the length of both of those ropes. So the first part of the problem was figuring out that the minimum cost is connecting all the ropes together, starting at the smallest ropes. So taking the 2 smallest ropes, connecting them. Then taking the next 2 smallest ropes and connecting them. And keep on doing that until you only have 1 rope. Once you understand that, then the question is, how do we get that? How can we implement that? And last week, we conveniently learned about a data structure that you could take the top element, and it was the highest priority, the largest or the smallest, depending on if it's a max or min heap. So we can use priority queues to figure out the 2 smallest ropes at any given time and connect them. Such a solution would look something like this, where we have a while loop. Well, first we declare a priority queue. In that priority queue, we use the greater comparator. And it's kind of confusing, but the greater comparator means that it's going to be a min heap, kind of the opposite, right? So if you want a max heap, if you want the largest element on top, you'd use the less. If you want the minimum element on top of the priority queue, use the greater comparator. Why is it like that? I don't know, just something to know. Then once you have that comparator and the minimum element is on top with this min heap, we just run a while loop. We throw it all into the priority queue, all the ropes, and then we say, while there's more than one element in this priority queue, we're gonna pop off the top two, connect them, record the cost, and keep on going. So that is the optimal solution. And what is the complexity of this solution? I'll ask you guys that. What is the complexity of the solution? Anyone?
And login.
Yes, n log n. And we can get that because we can take the complexity of all the individual operations. First, we can take the complexity of the priority queue, filling that up with the range-based constructor, which is going to be O of n. Remember, we learned last week that when you heapify, if you go bottom up, calling fixed down, you can do it in O of n time. Then we have this while loop that runs while the size of the PQ is greater than 1. The initial size of the PQ is going to be n. And every time you're decreasing the size by 1 because you're connecting 2 ropes. So this is going to run O of n times. And within here, we're going to do two pops and a push. Each one of those operations is log n because it's log of the size. So it'd actually be 3 log n. As you know, 3 log n, same thing as log n is terms as complexity. And then, so we would, because we're inside this while loop, we would multiply log n to n to get n log n for the total complexity of this, right? Because those log n's are nested in the while loop. Any questions on that? Bit of review from the complexity chapter plus last week with priority queues. So a good question is we can do priority queues, get this in n log n. Why not just use a sorted array? All we're trying to do is get the 2 largest ropes, right? So if we sort the array, where the array consists of the ropes, then we just take the 2 rightmost elements. Those are the 2 largest. Do you guys agree? Disagree?
Agree.
So is there anything wrong with this approach?
We'd have to sort.
You have to sort. And what is sort? I guess what is the complexity of sort? Well, it's n log n. So is this any worse than our other solution using priority queues?
Wouldn't you have to also, like, because you would have to sort it and then, oh, well, I don't know. Never mind.
No, you're onto something here. So yes, for the initial time, it works. We can just take these 2. And that's O of 1 if we have a sorted vector. But what about this push? What is the complexity of push? I guess the complexity of push is log n, right? Because we can do a binary search. I lied. It is not log of n. Silly me. What is the complexity of inserting into an array?
Isn't it supposed to be constant time?
But remember that this array also has an invariant that it has to be sorted, right? Because if we're going to take the top 2 elements out of this array every time in this while loop, we need the array to be sorted. So we need to have this invariant that the array is always sorted. Well, if the array is sorted, we can find the location in log n time using a binary search, right? But once we find that location, we have to insert it. because we're not just inserting on the end here, right? Because it's a sorted array. We're inserting into the array, potentially in the middle. So if we're inserting, this into the array, potentially in the middle, yes, it would be log n to find where to insert it. But once we want to insert it, we have to shift all of the other elements down. So pushing or inserting into a sorted array is actually O of n. And that's where I got tripped up. I forgot about shifting the elements down. So if the push operation is O of n, and the while loop is O of n, then this sort of implementation would actually be n squared. So in this example, priority queue is a much faster time complexity than keeping track of a vector and just always having this invariant that has to be sorted, and you can just take the two rightmost elements when you want to pop it. Any questions on that? Cool. Midterm. What's going to be on the midterm? Here is everything on the midterm. I'm not going to go over it all, pretty much up until this point, plus next lecture. If you saw the Piazza post, strings are not going to be on the midterm. I believe that will be on the final. However, everything else is fair game. Everything we covered in lecture is fair game. Everything on the project is fair game. All of you have done the projects yourself, so you're prepared in that regard. And hopefully you've been coming to lab. If not, there's recordings. But I would just recommend, as far as getting the concepts down, preparing for the midterm, I think the first step is just understanding the material. Go through your notes, go through the lecture slides, convince yourself that you understand the material. Once you understand the material, test yourself. Go through previous quizzes, lab quizzes, and see if you can convince yourself that you know those too. After that, I would start thinking about like the written, preparing for the written. Once you have a solid foundation of concepts. We're going to give you plenty of practice material, hundreds. I think it's like a packet of like 150 multiple choice questions. If you do all of those and understand all of those, you'll be more than ready for the multiple choice. For the free response, I think we give you a packet of like 10 previous free response questions. If you do all of those and you understand all of those, you'll be extremely prepared for this exam. So there's nothing to worry about. Just give yourself enough time. And you guys got this. Any questions on the midterm? Okay, cool. And one final note at the end of the day, this midterm is just an exam. 5 years from now, it's not going to matter what you got on this exam. What does matter, however, is what you learned in this class. So just remember, it's not really about the score you get on the exam, but whether or not you learned. Cool. Let's talk about types of containers. So there's two types of containers. You have searchable. There's actually a few, but two properties of containers is if it's searchable. And what that means is that you can look through the container. Use the .find operator. Two examples of this would be a vector or a deck, because you can, iterate through those containers and find an element. Example of something that's not searchable would be like a stack, because you cannot iterate through a stack. You can only look at the top element. So that's searchable. We also have sequential. And sequential means that you can iterate over the elements in some order. Kind of similar to searchable. A sequential container would be like a vector, because you can iterate through all the elements, or a deck. And something that's not sequential would be like a stack or a queue, because you don't have that ability to look at all the elements. They kind of go hand in hand. Like if you can look at all the elements, then you can search the container. Then we have two more properties. We have sorted and ordered. A sorted container means that the elements are stored in some predetermined way. So there's like one way, and this is kind of an important thing to note. There's one way to store them. Some unique ordering. An example of that would be like a set. You can implement a set using a sorted vector. All of the elements in that set have a specific location. Because of this, because everything has a specific location, you can't just insert anywhere you want, because that would break the sorted property. Sorted containers are convenient also because if it's sorted, if you have that information that it's sorted, you can easily find things quickly because you know where to look. So with a set, if you're using a sorted vector, remember in 280, you could use a binary search. We'll also talk about, I guess you already talked about maps. In maps with 280, and that was with the binary trees under the hood, you knew exactly where to look. If you had a value, you could find it by just iterating down the tree, looking at the keys. So that's sorted. And then finally, the fourth property that we're going to talk about for types of containers is ordered. And ordered just means that it maintains a specific order, or all the elements have maintained this relative ordering to the element to their left and their element to their right. Some examples of this would be like a vector. The elements in a vector don't randomly get shifted. If you have a specific element, everything to its left is going to stay to its left. Everything to its right is going to stay to its right, unless you obviously do some work on that vector and pop elements or insert elements. Any questions on any of these four properties? We have searchable, sequential, sorted, and ordered. Cool. We can look at ordered containers. And we could say that, if an array is ordered, insert would be O of n, because you have to shift the elements down, and then you got some other complexities. If you look at an array as a sorted container, which means that you're maintaining this invariant that the array is sorted, then the find operation would be log n, right? Because you can use the binary search. Indexing is still O of 1, deleting is still O of n, and inserting is still O of n in a sorted vector. Because remember, you have to shift elements when you insert or delete. And then we have put the complexities for the linked list too. Just looking at this table, do you guys have any questions on how a specific complexity was found? Common exam question, comparing arrays versus linked lists and their complexities. What if the array is sorted? What if the array is not sorted? What if the linked list is sorted? What if it's not sorted? And what are the complexities of inserting, finding, deleting, all of this? Cool. No questions. Either I'm very boring or this stuff's easy. So I hope it's the latter. Okay, so question for you guys. Multiple choice question on, kind of outdated now, the fall 2018 midterm. And this is kind of a confusing question. So before you answer this, I'll just preference this with what does it mean to be sorted? Remember, sorted means there's one specific ordering. And then I'll give you guys a second to answer this question. And then here's some definitions, just in case you forgot the previous slide. Ordered is elements maintain a relative ordering. Okay, anybody have an answer that they would like to share? All right, let's hear it.
I'm going to say B.
You want to say B. So you think that it is ordered, but it is not sorted. Why do you think it's not sorted?
I don't know.
And I'm not saying if you're right or wrong. I'm just curious what your thought process is.
So the reason I thought it wasn't sorted is because of the one unique order thing. And
Mhm.
I don't know. I don't really know the reason, but for some reason in my brain that's standing out.
No, you're totally right. So, and we can look at that too, because, and that this is a common misconception why it's not sorted. Because think about a heap. The only properties of heap is that the highest priority is on top, and that the parent is not a smaller priority than its child. So if we used, if we made two heaps for two max heaps, this would be a correct max heap, right? And in the array, that would look like 8, 2, 3. But you could also switch these 2 and this 3, and that would also be the correct max heap, and that would be 8, 3, 2. So you have the same exact elements. Both of them qualify as a max heap with two different orderings. Therefore, a heap is not sorted. There's two ways to represent the same heap, at least. So that's why it's not sorted, correct? But you did say that it was ordered. And I'm going to disagree with it being ordered, because think about it. Ordered means that elements hold some relative ordering with each other. So that, like, if I'm a specific element, all the elements to my left will stay to my left, all the elements to my right will stay to my right. But, and this is kind of confusing, I think I misled you guys earlier. When you insert, say, a new element into the heap, it calls fix up, right? So it can jumble up how the elements compare to each other as it fixes its priority in the heap. Therefore, elements don't necessarily maintain a specific order between each other, and it's not an ordered container. Let's see if I can give a quick example of that. Yes. Okay. So right now, for example, here is our heap. If I wanted to insert 4 into the heap, we would start right here, right? Then we would move it with 3. So it would look something like this, right? And I'm running out of space here. In the array, when we insert 4 into the bottom of our heap, what does the new array look like? Well, it looks like 8, 4, 2, 3. Notice how 2 used to be to the right of 3. Now 2 is to the left of 3. So by inserting a new element, we actually messed up the ordering of different elements in the heap. Therefore, it's not ordered. So the answer to this question, and it was a very tricky question, was actually D. And on that midterm, I believe the majority of the class got it wrong. Any questions on this one?
So for in terms of ordered, would the only ordered container that we know about right now, would it be linked list, because of the fact that it doesn't get, because what else doesn't get affected by insertion or deletion? Don't they all?
Yeah, so they all do get affected by insertion and deletion, but the idea is, say when you're take 2 elements and look at those 2 elements, when you insert into a vector, those 2 elements are still going to maintain a relative order. So if we have, this is our vector. Let's look at 2. 3 is always to the right of 2, right? Or it's currently to the right of 2. When I insert into this vector, no matter where I insert into the vector, say I could do here, 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 3 is always going to be to the right of 2. So inserting new elements does not affect the relative position of any element to another element. in the vector. Does that make sense?
Gotcha. Yeah.
Perfect. Pretty confusing definitions. But that's that. That's the answer. And then we're done with that. Cool. Let's go into sorting algorithms. Like I said before, it can feel kind of overwhelming, a bunch of algorithms. I'm going to try to alleviate that a little bit. It's really not that bad. And we're going to talk big picture. So what do you need to know with these sorting algorithms? Well, like we said, you need to know the underlying theory. You need to know the time complexity, the space complexity, how it works too. You know, is it recursive? Is it Taylor recursive? If it is recursive, how many stack frames could it have? Like worst case stack frames, best case stack frames, stuff like that. Average case stack frames. Stability. And the idea of stability is, you know, do all of the original elements maintain their ordering after you sort them? You know, if there's 2 5s in the container, and we sort it, does the previous left 5 still stay left of the other 5? Is it stable? That probably wasn't a good way to explain it. But, and then there's also adaptability. Whether or not, you know, some information on the stuff that we're sorting makes it sort faster. You know, if it's close to already being sorted, is the sort adaptive? Will it run faster than if it was all random and not sorted at all? So this is some good stuff to consider when studying for the sorting algorithms. And like I said, you don't need to know the specific implementation, the exact details. We're not going to expect you to implement these sorts on the exam. However, you should have a general idea of the pattern that it follows. Any questions on this before we go into the sorts? Cool. Okay. How many sorts do we have? There are 7. We have the 3 elementary sorts. Why are they elementary? Because they're O of n squared. Then we have the more advanced sorts. And what's the complexity of the more advanced sorts? Anyone remember? Average complexity of the more advanced sorts.
I'm behind on lectures, but I'm going to assume O of n.
O of n. One of them is O of n. You got that one right. Counting sort is O of n. Do you remember heap sort? We talked about that last week, where you heapify and then you sort the vector, taking the top element. The complexity of that.
Wasn't it O of n?
Well, O of n to heapify, yes. But then remember, you had to pop it n times. Each time you pop was log n. So n times the number of pops gave us n log n. You'll find that O of n log n is the best that you can get in a sort unless you have additional information, such as counting sort, where you know that the values of the elements can only, there's some upper limit on the value of the elements in which you can do O of n. Okay, and then you can use visual algo to visualize these sorts. All right, let's go into the sorts. Bubble sort, elementary sort. Basic idea behind bubble sort is that we just repeatedly go through the list comparing each pair of elements. And if you say the element on the right is greater or less than rather than the element on the left, we swap them. So you kind of just go through n times making swaps each time. So an example of this is, you know, if we had 2 pointers, a left pointer, a right pointer, we would first look at what the left pointer is pointing to 3. So we look at 3 and the element to the right, and we say, hey, if the element to the right is less than our current element, we're going to swap them because we want to sort this. So we look at 3 and 5. 5 is not less than 3. So then we go to the next one. We look at now the element to the right of 5 is 2. So we look at 5 and 2 and we say, yeah, 5 is greater than 2. So we swap them. And now we look at 5 and 6. And we say 5 is less than 6, that's fine. So we don't swap them. Then we look at 6, 6 is less than 7, that's fine. We don't swap them. And I don't know what happened here. Oh, that's our 5. So we went through one iteration, and we know that the last element has to be the rightmost element now, because we swapped all the elements if they were out of order. So now we can decrement this right pointer by 1 and repeat the process. Then decrement it again and repeat the process. So you can see you would implement this with like 4 loops, 2 for loops, and it's O of n squared. So let's talk about bubble sort. It's not used in practice. Why is it not used in practice? Because it's, first off, it's n squared, kind of slow, and it does constant swaps, which is kind of inefficient. It is stable, and what that means is, if you have 2 duplicate elements, the one on the right before it's sorted will stay on the right after it's sorted. The worst case is n squared. The average case is n squared because it's an elementary sort. But the best case is O of n. And the reason the best case is O of n is because it's adaptable. Anybody remember how bubble sort could be made adaptable? And remember, so you start with 2 pointers, one on the left, one on the right, and essentially you just keep on moving the one on the left until it hits the one on the right, and you swap 2 elements if the element on the right is greater than the element that you're looking at. Does anybody remember how to make this adaptable? So like here, we'd swap them because 3 is greater than 2. Here we want to swap, here we want to swap, here we want to swap. Okay, so quickly going over it, if any given iteration through the elements in your container consists of no swaps, then the list is sorted and you can stop there. So, if we have this sorted list and we try to, or array rather, and we try to run bubble sort, we could say like, hey, do we swap 2 with 3? No, we don't swap, we don't swap, we don't swap. If we never swap, we know that all the elements are in the correct final position. So it just takes one pass to figure that out. And that's O of n. So that's the best case. That's the adaptable case. To do that, we could just keep some sort of a Boolean and say like, bool has swapped equals false. If after one iteration, that Boolean is still false, we can just return out of the function. It's sorted. Any questions on bubble sort? Some interesting things about bubble sort is because you're swapping elements at every iteration, really, every element is getting a little closer to its final position every time, every iteration. So bubble sort is a great sort when all the elements are very close to each other, not close to each other, but close to their, say, final position. Say they are all off by 1 or something like that. Then bubble sort would be a good sort. But there's also other elementary sorts that would be a good sort in that situation. Also, it's a 1 memory because we can sort this in place. We don't need any additional memory. Okay, that's bubble sort. Now let's talk about selection sort. I think that selection sort, at least for me, was like the most intuitive to start out. So you have 2 pointers. One of them is like the current position. Let's say the orange one is our current position, and the blue one is finding the element to put there. So, our current position is the first element. So we want to find the smallest element to put here. So we just iterate through the rest of the list with our other pointer, and we find that smallest element. So find the current smallest element, and it ends up finding 2 after a linear iteration. So then what we do is we swap this position because our smallest element should go on the very left. Now that our smallest element's on the very left, we can increment this current position by 1. And now we find the next smallest element. So we once again use our blue pointer to find the next smallest element. It ends up finding 3, and we swap these two. Okay, and then we increment the third one, and we find the next smallest element. Then we figure out it's 5, so we swap 5 with itself, it's 5, and then we increment them. So because, for every element, we're doing a linear operation, it's also n squared. This is a little different from bubble sort because it's n squared average, n squared worst, but it's also n squared best because there's no adaptable variation that we covered. Similarly, O of 1 memory, we're not using any additional memory, and it's not stable. At least it's not stable in O of 1 memory. You could store some additional information to make it stable in O of 1 O of n memory. Any questions on selection sort? We say that it's good when ox memory is limited because it doesn't use any additional memory. It's also good when the things that you're swapping, when your objects, your elements are huge elements. Let's say that they were like class objects, like 50 or something bytes each. With bubble sort, you're making tons of swaps. You're swapping every element potentially n times. With selection sort, every element is swapped very infrequently. You're only making one swap every iteration of selection sort. So if your elements, like we said, 50 bytes were huge elements, minimizing the number of swaps might be ideal because swapping a large element, you have to copy over all of the member variables. So that could also be a situation where selection sort is good, is if you have large objects. Yeah, so that's selection sort. And then finally, the last elementary sort is insertion sort. And the way that you can think about insertion sort is like you have a sorted section and a non-sorted section. And every iteration, you're taking an element that's in your non-sorted section and finding its position in the sorted section. So let's start here. Our sorted section is here. Everything right here is sorted. Everything right here is not sorted. So we're looking at 5 at our orange pointer, and we say, okay, we're going to figure out where to put 5 in our sorted area. We look at 3, 5 is greater than 3, so we know it's good in our sorted area. Next, we increase the size of our sorted area, so now it contains 3 and 5. So this little subarray is sorted, and we're looking at 2 with our orange pointer. And with our blue one, we're finding out where to put 2 in our little sorted subarray. We end up figuring out that 2 would go in the very beginning. So we shift all these elements down and move 2 in the beginning. And now our sorted subarray consists of these 3 elements. And we reset our pointers to now point to 6. And now with the blue one, we figure out where 6 goes, it stays there. We go to 7, we figure out where 7 goes, it stays there. So that's the basic premise of insertion sort. When preparing for the exam, I think one good thing to do to try to understand these sorts is just to get a whiteboard. Look at the algorithm behind the sort and run through it yourself. Take this unsorted array and sort it with all the sorts, stepping through each step. If you can do that and you can figure out, the underlying idea behind each sort, it kind of helps you visualize it. And then you can easily, answer questions more on the conceptual side. So that's insertion sort. This is our last elementary sort. Average, worst case are both n squared. Uses a nested for loop. Memory is still in place, O of 1. And this one is stable. Its best case is also O of n, which we talk about, and that's the adaptive version of insertion sort. Actually, not even adaptive. The reason, if your vector is already sorted, yeah, there's an adaptive version. We go over like multiple ways to implement insertion sort in lecture, and you can get down to O of n if you keep some sort of a Boolean flag. Or just stop iterating the nested for loop if it's already in its final place. So yeah, best case for insertion sort is O of n when the array is already sorted or very close to being already sorted. And this is interesting. Insertion sort is actually in implementation one of the fastest sorting algorithms on small inputs. So if you have, say, like 10 elements, insertion sort might actually run faster than like an n log n sorting algorithm. Any questions on insertion sort? Cool. Okay, so those were the three elementary sorts, and they're elementary in the fact that their worst case and their average cases are n squared. Best case for two of those sorts is O of n, and that's because they're adaptable on nearly sorted arrays. And all of those sorts are O of 1 memory, additional memory, because you can sort them in place. Now let's talk about merge sort. So merge sort is a more complex sort, and it's better than n squared. And the idea about merge sort is, I believe you guys actually haven't gone over this in lecture yet. I think it's tomorrow's lecture. So I don't want to go too far and confuse you, but it uses recursion. Or did you guys already go over merge sort? Either merge sort or quicksort, one of those you haven't done yet. Anyone up to date on the lectures? I believe merge sort is the one that you haven't covered.
I'm like not behind, but I think the professors are like really behind.
Okay. Yeah, I know that this semester they gave themselves an extra lecture.
Yeah, in Darden, like I don't think we've covered any sort, but I might be wrong.
Any sort or any non-elementary sort?
Any sort at all.
Oh no, so this is probably really confusing then. Then maybe like watch this lab again when you do cover everything too. Yeah, if you're learning this for the first time, I apologize. This would probably be pretty confusing. But okay, so big picture merge sort. So the idea of merge sort is that you're using recursion. And essentially it says, I'm gonna look at this entire array and I'm gonna split it in half. I'm gonna split it into the left side and the right side. I'm gonna then sort those sides. And once those sides are both sorted, then I can easily merge them back together in O of n time. So like a big picture, if we were looking at this giant array, our first stack frame, because it uses recursion, let's say it's blue. Blue's going to say, okay, we're going to break this in half. We're going to sort this side. We're going to sort this side. And then we're going to, combine them together in O of n time. And then it's all sorted, right? So that's what the first stack frame says. Well, how do you sort those two subsections? Well, you call the same thing on the subsections. So our first stack frame says, once we sort those two halves of the array, we can combine them together and we have a sorted array. I guess everybody agree with that. Our first stack frame, it says if this is sorted and this is sorted, we can combine them in O of n time. You can combine two sorted arrays in O of n time, and the whole thing will be sorted, right? True. Perfect. So this first stack frame says, once you sort this stuff, I'll combine it. So now we go into another stack frame. And this stack frame starts on the left side. And it says, okay, I got to combine this left side. I want to sort this left side. So what am I going to do? Well, if you sort those two halves of mine, because it's looking at all this now, once you sort those two halves, then I'll combine them in O of n time. Okay, but those two halves aren't sorted. So then we get to a red condition, a red stack frame. And this red stack frame is just looking at these two. And it's saying, sort those two, and then I'll combine them. Well, those two are already sorted. There's only two elements, right? So we could just combine them now, in O of 2 time. Make it look something like this. So this little subarray is sorted now. So that stack frame finishes. And then we go into a purple stack frame, remember? Because orange said you gotta do both sides of mine. So this purple stack frame says, I gotta sort this. But my two subarrays are already sorted. There's only two elements. So you combine them and then you return. And now we get back to orange. In orange, those two subarrays, those two halves are all sorted now. So now I can combine them. So now orange is like perfect. The orange stack frame is like perfect. I can combine these two halves, and make it look something like this. Ooh, that's too big. And now this orange subarray is sorted. Perfect. But remember, blue needs a requirement. This blue stack frame, we can get out of these two stack frames. Gone. This blue stack frame needs the requirement that both sides are sorted. So there was now another call on this side to sort it. That side says my two subarrays need to be sorted. So it makes two more calls. Like let's say one here and like one here to sort those two subarrays. Eventually, these two small calls return. This subarray gets sorted. That subarray gets sorted. Then it returns to the green stack frame, which then says, okay, my two halves are now sorted, so I can combine them together. To combine these together, it would look something like this. Good. And now we return to that giant blue stack frame that says, first sort my two halves, and then I can combine them. Well, now the two halves are sorted. So it can combine them in O of n time. So the idea is you're recursively breaking the vector into smaller and smaller subarrays until you get to this base case. In our case, when we had one or two elements where we can just sort those quickly. And then we slowly build back up and just sort the entire thing. Each step of the algorithm takes O of n time to, well, actually, let's talk about that. So here is our code right here, where left and right just refer to the boundaries of our array at the current position. So the left will refer to the left bound, right will refer to the right bound. That's just like what our array currently is. For the subarrays, those bounds get smaller and smaller. And what we do is we call merge sort on the subarrays, and then we merge them back together. Merge sort is a recursive call. So you can think of this like T of n divided by 2, because we're calling it on half of that array. So you're making two recursive calls, and then we're calling merge, which is just combining two vectors, which is O of n. So if you look at this, review of our recurrence relations lab, we can look at this as T of n equals 2T n divided by 2 plus n. Then when you see that, you can say, hey, I can run the master theorem on that. And when you run the master theorem on this recurrence relation, you get n log n for the complexity. So once again, merge sort is just saying, sort my subarrays, the left side and the right side, and then I'll combine them together. And it keeps on saying that until all the subarrays get sorted, then it combines it all together. And the complexity of merge sort is because you're making 2 recursive calls and doing O of n work in every call gives you complexity of n log n. I'm sure when you have like an hour and a half lecture on that, it's going to make a lot more sense. Or an hour lecture. Okay. Or I guess hour and a half. Okay, so merge sort, like we said, the average case is n log n. Turns out the best case, the average case, the worst case, they're all n log n. Memory. Additional memory, it uses O of n additional memory. The reason it uses O of n additional memory is because when you're combining 2 arrays, a common implementation, a simple implementation would, create an array to combine them into. So the O of n additional memory comes from the combine step. And it is a stable sort. You can also do merge sort bottom up. The example we just went through was top down using recursion. You can do it bottom up as well. The bottom up way to do it does not, I believe you can do it in place in O of 1 memory. But this example is O of n memory. And yeah, so merge sort is our first recursive sort that we went through, and it's n log n. Any questions on that? Once again, if this is the first time seeing it, it's probably really confusing. But maybe this will be like a good intro for the lecture. Cool. And chat mentions that CS50 lecture 3, which I assume you can find on YouTube, helps a lot with sorts if you want additional information. Okay, so that was merge sort. Now let's talk about quicksort. So quicksort is kind of like merge sort in the fact that it's also a recursive sort. And let's just quickly go through one step of quicksort. So maybe in lecture, you talked about this sort. The first thing we do is we pick a pivot. And the way that we picked our pivot was we just took the very right side, so 4. And now that we picked our pivot of 4, we have 2 pointers. One to the beginning of the array and one just to the left of 4. And we increment this pointer every time the value is less than the pivot, and we decrement this pointer every time the value is greater than the pivot. If that's not the case, we swap them. And we continue to do this until the 2 pointers meet. So right now we're looking at 5. 5 is not less than 4, our pivot, so it stays there. Now we're looking at 1. 1 is not greater than 4, so it stays here. Now that they're both there, we swap those 2 values. Okay, and we continue. So now we move this to 3. 3 is less than 4, so we continue. Now we're at 7. 7 is not less than 4, so we stop. We're still at 5, so we swap because 5, no, we don't swap. We decrement because 5 is greater than 4, our pivot. 5 is still greater than 4. 6 is greater than 4. 2 is not greater than 4, so we stay here. So now that we stopped moving both pointers, we swap what's at the pointers. So 2 and 7. Okay, now we go back to our left pointer and we increment it because 2 is less than 4. And here we go. The pointers are both touching the same element, 7. And at this point, we swap our pivot with the element that they're touching. So we would swap 4. Oops. Oh my gosh. We swap 4 with 7. And what this says is now you can notice that our pivot, which was 4, everything to the left of it is now less than it, and everything to the right of it is now greater than it. So if we keep on doing this, picking new pivots, One of the pivots we would pick would end up being this one because it's to the right of our previous or left of our previous pivot. And we'd also pick, I believe we'd also pick 7. Yeah, we'd also pick 7. So those would be our next 2 pivots. And we'd repeat the process with the subarrays. And every time that we pick a pivot, we end up essentially swapping all the elements in that subarray so that everything to the left of the pivot in the final position is less than it, and everything to the right of the pivot is greater than it. Yeah, and that's all I'm going to say about the pivots right now. Okay, so how does this performance go for Quicksort? The average case is n log n. That step that we just ran through was O of n, right? We picked a pivot, then we shifted everything to the left of it to be less than it, shifted everything to the right of it to be greater than it. That was an O of n operation. Ideally, you only do log n of those. So our average case is log n. Or our average case is n log n rather, because each step is O of n work. Worst case, however, is if we pick really bad pivots. Say that every time we pick a pivot, it's the smallest or largest value. So we end up swapping nothing else. We're not doing any work with moving that pivot. The worst case actually comes out to n squared if we get very unlucky. And then how much memory does it use? It uses log n memory. The reason it's log n is because this is recursive, and log n refers to the number of stat frames. It's not stable, and the best case is also n log n. So when you look at this sort, Quicksort, you say the worst case is n squared. With merge sort, the worst case was n log n. And the average case for both those sorts are the same exact thing. So how is this a competitive sort? You know, its worst case is worse than the other one. Its average case is the same. Why don't we just choose the other one? And this kind of goes back to complexity just tells you, you know, how it scales. Quicksort is actually one of the fastest sorts because this worst case barely happens. And that average case, the average case is a constant factor faster than merge sort. So in practice, this sort is actually typically used. The STL, I believe, actually uses Quicksort. And then if it notices, it's adaptive. If it notices that it's starting to get to that worst case scenario for Quicksort, where it might end up being n squared, it switches to a different sort that has a worst case n log n. So it might be like Quicksort, Quicksort, Quicksort. Oh no, heap sort. But typically, you know, since the worst case barely ever happens, it'd be like Quicksort all the way through. And then maybe once it gets to a small enough input, it'll actually switch to insertion sort. Because it'll be like, oh, I only have 30 more elements to sort. I know that insertion sort, even though it's an elementary sort, it's really fast on small inputs. So I'll run that one over Quicksort. So the STL is like optimized to actually run like different sorts depending on how it's reacting to the input. I don't think you need to know that, but it's just interesting. It shows an example of like situations where like runtime complexity or runtime might differ from the theoretical complexity. So it's often faster in practice than other n log n sorts. And that worst case, once again, is n squared. And that's when you pick really bad pivots every time. So let's talk about Quicksort. What causes the worst case behavior? This one's for you guys. So how do we get that n squared behavior?
When you choose bad pivots.
When you choose bad pivots. And what is a bad pivot? Let's say that every time you pick a pivot, you're either picking the largest or the smallest pivot so that you end up swapping no other elements. Because if you look at Quicksort, really what you're doing is every time you're picking a pivot, you're kind of shifting around the other elements to be closer to their final position. And if you're never doing that, every time you pick a pivot, you're not doing any additional work, you're going to get the n squared behavior. So I think it says when you pick the largest or smallest element every time. So what's the ideal pivot then? How can we optimize the amount of work that we're doing every time we choose a pivot? 4 was a pretty good pivot, right? Because, you know, when we had 4 as our pivot, we ended up shifting all of these elements to be closer to their final position, shifting all these elements to be closer to their final position, because there's a lot of elements less than 4 and there's a lot of elements greater than 4. So what would be an ideal pivot? And you might also cover this in lecture. An ideal pivot would be the median of what you're trying to sort. But kind of interesting, in practice, well, actually, so this might sound confusing now, but I think this is pretty interesting. And maybe when you watch this, when you're reviewing for the exam, you'll get a pretty good idea of this. With Quicksort, you know, every step of Quicksort takes O of n time, right? Because we had 2 pointers after we picked our pivot and we ended up iterating them all the way through the vector. You can actually find the median of an array, an unsorted array, in O of n time. So a good question might be, wait, if I can find the median of this unsorted array in O of n time, and I already know that this operation is going to be O of n, why don't I just always find the median and then use that median as the pivot rather than just picking, you know, the last element to be my pivot? Because if I can find the median O of n time and it's already O of n, you know, I'm not losing any complexity. I'm not decreasing, or I guess increasing the overall complexity by finding the median. So why don't I do that? Why do I just use this random, arbitrary last element as my median? Cool, we got some answers. All right, yeah, sure, Jake.
Yeah, I'm just gonna take a guess here, but
Sure.
don't you have to apply the median finding O of n for every single like step of the splitting it in half? So that would, you have to apply that like log n times, right?
Exactly, you would have to apply it log n times. But remember, we also have to apply iterating through the entire array already log n times. And iterating through the array is O of n. Like with our pointers, when we're shifting elements to be less than and greater than the pivot, we're starting at the back and the front of the array. That's still going to be O of n. So I guess my question is, to find the pivot, it's O of n. Doing that is O of n. These would be sequential. They're not multiplying. So it would be, you know, O of n versus an extra, maybe O of 2n for each step. Both of those are still O of n. And this once again comes down. So actually, so let's say that you did do this. You found the median every time in O of n time, and then you did the pointers. That would then, if you're finding the median every time, you would no longer have a worst case. It would always, worst case would be n log n if you found the median every time, because you no longer would pick a bad pivot. You actually pick the perfect pivot every time. So the reason why we don't find the median, why we don't do that O of n additional work to find the median, goes back to the idea that runtime and complexity aren't necessary. Complexity is not necessarily the best measurement of runtime. So even though you could do O of n additional work to find the median, in practice, it's much more rare to get that worst case scenario. So just by doing random sampling and finding the median in O of 1 time, which is going to be a constant complexity faster than it would be to use a constant factor complexity faster than it would be to use the median. Because you can do that in the worst case is very, very rare. It's actually like typically faster in practice just to random sample and hope for the best. So worst case barely ever happens. It turns out the algorithm is like significantly faster just to random sample and not find the median. So pretty interesting. If that's confusing, don't worry about it. Okay. So summary of the sorts, everything that we just covered, all the complexities of each sort, the memory, the stability, the adaptability, all in this table. Great resource, for a cheat sheet for the exam. And that's the sorts. So one final thing in this lab, we're going to talk about binary search. Binary search is a classic problem for interviews, and we're just going to cover one problem on it. Remember that you can use a binary search when you have some sort of information that like the array is sorted in some order. Okay, so here's our question. We're given an array that is first increasing and then decreasing. And we want to find the maximum value of the array. So you can see here that this array increases up until we get to 400, or actually 500, increases up until we get to 500, and then it decreases. And we want to find 500. This increases to 50, then it decreases, and we want to find 50. Obviously, you could figure this out in O of n time just by iterating over the array and finding the max value. However, we want to see if we can figure out a way to find this in faster than O of n time, if we can use a binary search to find out the max element. So I don't think we should go over the implementation, but with binary search, what I want you to tell me, what I want you guys to figure out is, given an element, the middle element, how do we know whether or not we want to look to the left of the vector or the right of the vector? So for example, say that we're looking at like 20. How do we know if our final answer is going to be over here, over here? That's going to determine, where we're going to adjust the binary search to look into that sample, that sample space. So anyone have any ideas how we can use a binary search to figure this out?
The number we're looking for is bigger or smaller than the current number?
If the number that we're looking for is bigger or smaller than the current number. Yeah. So yeah, that's a good initial idea. So with binary search, I guess, just to refresh on 280, what you do is our array is essentially initially this big, and we look at the middle element, right? And from that, we either decrease our array to be like that big, where we look at all these elements in the future, or we decrease the array to be this big, where we look at all those elements in the future, and then we do a binary search on that subarray. And we keep on doing that until we find our answer. So I guess, how do we know the element that we're looking at? How do we know when we found our answer? So let's say that we're looking at 200. How do we know if 200 is the answer? If that is our maximum value? And we can stop.
You could look at the left and, well, I don't know if it's assorted or not, but you can look at the left and right nodes and then see if there's a, like the right one is smaller than the left one.
Exactly. So we want to find the maximum value, and we're given that the array first increases and then decreases. So we know that, once you can kind of imagine this like a mountain. You know that we found our maximum value when to the left of it is smaller and to the right of it is also smaller, right? So when we see 500, we know this is the max because to the left of it's 400 and to the right of it's 300, or not 300, 3. So we could stop there, if left L and right L are smaller, we're done. So that's like the initial check with our binary search. Now, how do we know whether or not to go to the left side versus the right side? So let's say that this isn't the case, that the left L and the right L are not both smaller. How do we know whether to break our subarray to the right or break it to the left, go to the left or go to the right? Hint, it also uses the neighboring elements.
Yeah, so if the right one is bigger, then you go towards the right, and then if the right one is smaller, you go towards the left.
So you're saying we can just, let's say we're putting at 200, we only have to look at the right element. If the right element is larger than our current element, then we know that the answer must be on the right side. If the right element is smaller than our current element, then it must be on the left side. I agree with that. So, if left and right are both smaller, we're done. We found our max element. Else, look at the right element. If larger, go right. Smaller, or else go left. And yep, so that's the basic idea. Once you understand with these binary search problems, once you understand what you're doing when you're looking at a specific middle element, you know your terminal condition and you know how to get to the left, when to go to the left versus when to go to the right, then you pretty much know how to solve the binary search problems. Then it's just like implementation. So from here, this is just pseudocode. You could implement it yourself using like left and right pointers. And while like left doesn't equal right or whatever. So that's binary search. This is a medium question on LeetCode. If you want to try it out yourself and see if you can do the implementation, number 162. So it's a pretty hard question. And that's really all I have for you guys. Quickly with the handwritten problem this week, you're given an array that's unsorted. And you're given that it only contains the values 0, 1, and 2. And what you have to do is you have to sort the array in O of n time. So you might say, oh, 0, 1, 2, that sounds like counting sort. The max value is 2. That's a discrete value. For the upper bound, I can use counting sort in O of n time. You could, but we also require that you use no additional memory. So O of n time, O of 1 memory. So unfortunately, counting sort will not do that for you. Then, and that's that. So maybe a hint for this is think about left and right pointers. Maybe one starting at the beginning and one starting at the end. That's lab. Once again, good luck on the exam. I believe in all of you. And yeah, thanks for coming.
Thank you.